Greetings to you. Welcome to Physics with Ben. Don't forget to subscribe and share this video to those that need it. In today's video, we want to look at galvanometer conversion. This is a galvanometer. That is to say, we want to look at how we can convert a galvanometer into an ammeter. How we can convert a galvanometer into a voltmeter. So let's begin. Conversion of a galvanometer into an ammeter. We call it shunt. By the way, what is a galvanometer? A galvanometer is a very sensitive electrical device that is used in measuring very small amount of current. It measures currents in milliamps. That is milliamps. That is 10 raised to the negative 3 amps. That is how it measures current. Now, you'll be wondering why you have this guy stationed at the center, and then you have this way, and you have 35 this way, and then 35 this way. If I draw a sinusoidal wave function, and I write this, I draw a transverse wave here. The point where this galvanometer is right now, this is the point. If it races this way, that is clockwise. Let's say this is plus 35. This is minus 35. So this, if it goes this way, this is the maximum point. This is the maximum displacement, the maximum deflection. If it comes this way, that is, if it turns to the left, this is what we call it minimum deflection of the galvanometer. It simply works with the principle of electromagnetic induction. But we are not looking at that into today's video. So let's go straight to the point. Conversion of a galvanometer into an ammeter. Before me, this is an ammeter. An ammeter is an instrument that is used in measuring electric currents. Here is a voltmeter. This is a voltmeter. A voltmeter is an electrical device that is used in measuring potential difference in the circuits. Before we go into this topic proper, I would like to give us some basic knowledge that are very, very imperative for us to understand this topic comprehensively. For you to understand galvanometer conversion, please note the following. Number one, you need to revisit connection of resistors in series and in parallel. You need to revisit that topic. Recall that when resistors are connected in series, we have the same current flowing through them. We have different voltage across the resistors. This is what I mean. If you connect resistors in series, we can call this R1 or R2 or R3. Now, if this is terminal A and this is terminal B, and the current is passed through these terminals, let me draw a complete circuit. This is my battery, this is the plus side and the negative side, and this is the voltage across R1, this is the voltage across R2, this is the voltage across R3. The voltage across R3. So what I'm saying is this: the current will flow in this direction, then back to this place. In this kind of arrangement, the resistors are in series. The same quantity of electric current or charge will flow through them, while you are going to have different voltage across the resistors, and that's why you're having V1, V2, and V3. This is V3. This knowledge is very, very basic in understanding galvanometer conversion. Similarly, if we connect, alternatively, if we connect resistors in parallel, what do you expect? If we connect resistors in parallel, something like this. Then something like this. And let's say this is terminal A and this is terminal B. This is the voltage, and this plus, this is negative. The current will flow this direction, will flow here, will come in here, and this is the current I. And then we'll go here, pass this way, back here, this way, we come out here, down, and back to this place. In this kind of arrangement, you are going to have this is your R1, this is your R2, this is your R3. In this type of arrangement, you're going to have I1, I2, and then I3. However, the total voltage that is generated at this point will flow through each of the resistors. In summary, what you have here is this: you have different currents flowing through resistors when they are in parallel. Then you have the same voltage across the resistors when they are in parallel. So these are the knowledge that you need in understanding this topic. Number two, you need to make use of Ohm's law. You know that V is equals to IR. We are going to use this equation to customize all the equations in galvanometer conversion. So it is time for us to begin now. I believe this has well informed you of what you be expected to do in this topic. So let's begin the conversion program. Conversion of a galvanometer into an ammeter, we call it a shunt. How is that done? Right. A galvanometer can be made to behave like an ammeter, or a galvanometer can be converted into an ammeter when you connect the galvanometer in parallel with a very low resistance wire called a shunt. Now, what I just said, this is what it means pictorially. We can look at this as a shunt. The very low resistance wire in question as a shunt, and we can choose this symbol for the galvanometer. Line here and then the line here. Let's extend this line, and then we can join this line and then join this line. So let's look at this as terminal A, and this is a terminal B. There is a junction here. Now this is the resistance for the shunt, Rs. Please follow me. RS stands for resistance of the shunt. So this symbol inside the galvanometer is the internal resistance of the galvanometer. The internal resistance of the galvanometer is very, very high. It is in line to that the galvanometer is capable of measuring very, very small amount of current in milliamps. So we write this is the resistance of the galvanometer, Rg. Now, I told you that when resistors are connected in parallel, you have different current flowing through them, while you have the same voltage flowing through them. So let's assume that current is supplied at this end. We call it IT. The current supplied at this end is just IT. And then this wing, this arm, is the current entering into the galvanometer. We call it Ig. And this wing is the current entering into the shunt. We call it Is. Now, we are not done yet. We said that in such arrangements, you are going to have the same voltage throughout the circuit, because this guy and this guy, they are in parallel. So you are going to have the same voltage across them. Now, we are going to state Ohm's law, and then from there, use the law to customize all the equations in this topic. Now, right, from Ohm's law, V is equals to IR. We call this equation number 1. Now, the total current flowing through this circuit is given as IT is equals to Ig plus Is, right? So we say that IT is equals to Ig plus Is. Call it equation number 2. Now, I forgot to explain what a shunt is. A shunt is simply a very low resistance wire that is connected in parallel with a galvanometer to make it behave like an ammeter. The end result of this arrangement is for us to get something like this. And you can also agree with me that this is not only the symbol for the galvanometer. You can choose a symbol or choose a G with an arrow, but I choose to make use of this symbol. So let's move on. Now we are going to write again. Now let's look at this as voltage, the voltage of shunt. Vs, that is the voltage of shunt, and then this wing, we call it the voltage across the galvanometer. The voltage across the shunt, let's write it here, the voltage across the shunt, and then we have here as well the voltage across the galvanometer. But mind you, we said that we are going to have the same voltage throughout the circuit. So we'll write again. From here we write that Vt is equals to Vs is equals to Vg. Call it equation number 2. I believe you are following. Good. Now it is time for us to customize this equation now. From Ohm's law, we can now write, we want to generate the equation for the shunt. Because there are times the examiners will ask you to calculate the value of the resistor that is connected in parallel with the galvanometer to make it behave like an ammeter. They are simply asking you to calculate the shunts in the circuit. So we are going to customize equation number 1 right now. So let's write. We say that Vs is equals to Is times Rs. call it equation number 3. This is equation 1, 2, 3. This is equation number 3. And this is equation number 4. Now, but Vs is equals to Vt is equals to Vg. Again, from this equation, we know that Vs is equals to Vt minus Vg. So, again, we know that Is is equals to Vt minus, It minus Ig. So, we are going to take the whole of this and put it in here. So, this implies that Vs is equals to It minus Ig times Rs. We are going to make Rs the subject of the formula, the resistance of the shunt. So this implies that Rs times Ig is equals to, Rs times It minus Ig is equals to Vx. We divide both sides by It minus Ig. It minus Ig. This we cancel this. Therefore, the resistance for the shunt Rs is giving us Vs divided by It minus Ig. You can call this equation number 5. Equation number 5. If you still want to go on to get more advanced equation from here, you know that from V is equals to IR. The equation for Ig is Vg is equals to IgRg. So this implies that your Ig is equals to what? Vg over what? Rg. So this equation can also be written as the resistance of the shunt is equals to voltage across the shunt, which is the same thing as the voltage supplied in the entire circuit, divided by It divided by It, yes, total current in the circuit, It minus Vg divided by Rg. So we can call this equation number 6. So these are the available equations for converting a galvanometer into an ammeter. We call this the shunt. Are we good? Look at it very well, and then we can continue from here. So now I want to look at how to convert a galvanometer into a voltmeter. I believe I can play this right now. Yes, I can. Okay, conversion of a galvanometer into a voltmeter. We call it multiplier. A galvanometer can be made to behave like a voltmeter, or a galvanometer can be converted into a voltmeter when you connect the galvanometer in series with a very high resistance wire called the multiplier. Pictorially, this is it. You draw a circuit like this, and then you have something like this. Another one. This time, let's choose a G. Let's choose the symbol now for the galvanometer. We're still correct. And then let's try to bring this line down. Down. So let's put this as terminal A and let's put this as terminal B. Yeah. Now, this is the resistance of the multiplier and this is the resistance of the galvanometer. And then from this point to this point, this is the voltage across the multiplier. And from this point to this point, this is the voltage across the galvanometer. That's it. Now, there's a current coming in here, we call it IT. Now remember from the beginning of this video, I told you that we need to take notes of the behavior of current and voltage when resistors are in series and in parallel. That we are going to apply that knowledge here. Now, the resistance of the shunt, the resistance of the galvanometer, these guys are in series. They are going to have the same current flowing through each of them. So this is, although we have Im, we have also Ig here. We write from Ohm's law, right? From Ohm's law, we have V is equals to IR. Now let's suppose that this is this circuit is supplied with the current will flow down here, go this way, here, this way, or this way, and then we plus out. So let's suppose that this is the total voltage that is supplied in the circuit. Maybe somewhere here. Yeah. This is the total voltage that is supplied in the circuit. Maybe somewhere there. Now, in this arrangement, we write that the total current IT will be equal to Im and will be equal to what? Ig. Call this equation 1, call this equation number 2. Now, the total voltage in the circuit, Vt, is simply the sum of the voltage across the multiplier and then the voltage across the galvanometer. So we say that Vm plus what? Vg. Vm plus Vg. That's it. So we are going to customize that equation now. We are going to customize Ohm's law equation. Now, we want to generate the equation for the multiplier. Right. We want to customize equation number 1. So this is equation number 3. Equation number 3. So we write Vm, voltage across the shunt from Ohm's law, this equals to IR. This equals to ImRm. We write, but what? Im is equals to It is equals to what? Ig. It doesn't matter. So we can choose to use It here or Ig here. So if you are faced with a question where the current in the galvanometer is given to you, then you can use that current to substitute here as your Ig or your It or your Im. It's the same thing. So we write again. How about Vt? Vm will now be Vt minus Vg. So we say that Vm is equals to Vt minus Vg. That is it. Vm is equals to Vt minus Vg. So we substitute this equation back to this here. So we have this implies that Vt minus Vg is equals to ImRm. We want to make Rm the subject of the formula, so we write. We have ImRm is equals to Vt minus Vg. So we divide both sides by Im. This we go, this we go. Therefore, our Rm is giving us Vt minus Vg divided by Im. We call this equation number 4. Equation number 4. As I said earlier, if you see one, you can still go back to this equation Ohm's law and generate the equation for Ig, for Rg. You know that from Vg is equals to IgRg. We want to get rid of Vg in this equation. So you are free to say that Rm is equals to Vt minus IgRg divided by Im. We call this equation number 5. See the same thing. Equation number 5, see the same thing. If you don't want, you can still go ahead and make Vt the subject of the formula. You know that Vt is equal to what? Vt is equal to what? Vm plus Vg. So you are free to say that Rm again is equal to what? Vm plus Vg, bracket, open bracket, close, minus IgRg, all divided by what? Im. You can call this equation number 6. So this is how to convert a galvanometer into a voltmeter, called the shunt. To this, we have come to the end of today's video. The next video I'm going to make on this topic would be calculations on galvanometer conversion. Don't forget to subscribe to my channel. God bless you. Bye-bye.